Okay, we are looking at our second video on circular motion, and we'll do some more special cases of centripetal acceleration. So let's say I've got a ball, and there's just one ball rotating around in a string. And let's say we freeze that rotation in 4 different places as shown here. So each one of these balls represents the ball being frozen at different positions, and we're going to look at the velocity. Now we're actually going to do this in a vertical circle. So imagine a ball on a string rotating around in a vertical circle. So there are 4 special places where we want to look at it. And we want to calculate the tension force in the string. So always the tension force will be pointing towards the center of the circle at all locations here. So there, pointing there, there, and there. Okay, so let's take a look. At the very bottom of the circle, the force tension, again pointing upwards, has to go against gravity. So gravity is straight downwards here. That's force G there. So the force tension here has to do 2 things. It has to pull the ball against gravity and also provide the circle. So the force tension at the bottom is going to be a sum of force gravity plus force tension, because the string has to do both, make the circle happen and also hold the ball up from gravity. At the sides, in either location here, force tension is going to be perpendicular to gravity. And you would know by now that things that are perpendicular have nothing to do with each other. So at the sides, force tension is just equal to force centripetal. Okay, so on this side as well, force tension equals force centripetal. Okay, now at the top, we have force gravity pointing downwards in the same direction that force tension is pointing in. So force tension is getting some help to keep the ball going in a circle. So at the top, force tension is equal to force centripetal minus force gravity. Because again, the gravity is pointing to the center of the circle, and you kind of think about that. That's allowing the string there to not have to pull as much to keep the ball going into a circle. So that's kind of how that works. A good application of this is a roller coaster. So a roller coaster going down a hill, at the bottom here, the force of the track pushing in this direction here, okay, when the cars are there, is going to be equal to the force centripetal plus force gravity. So the track's got to do a lot more pushing at the bottom. When the cars get to the top here, again, we've got force gravity pushing downwards. And of course, the track then doesn't have to do as much to keep things going into a circle there. So the force of the track here is going to equal force centripetal, okay, minus force gravity. Okay, so you get an idea that, you know, we can see less, okay, of the force of the track that it actually has to do at the very top here. Now, if by chance force centripetal equals force gravity, okay, then the force of the track is 0, and that's what a 0 gravity hill feels like. Your stomach gets that kind of weird feeling in it. So you're kind of like freely floating around that circle just for a moment. So that's part of the magic of roller coasters. Of course, there are some roller coasters that, you know, do the loop-to-loop. They do a nice loop like this. And you would have the same kind of conditions there. At the bottom, there's the greatest force. At the top, there's the least amount of force. So you get that really weird feeling as you go around, as gravity effects change around the whole circle. Okay, now what about going into outer space? Well, when you go far away from the Earth, the gravity is no longer, force gravity is no longer simply m times g. So we have to use what's called Newtonian gravity. Okay, so when you're far away from something, you've got to use this formula. Force gravity equals g m1 m2 divided by r squared. Now, r is measured, and I'll do brighter color here, from the center of the Earth to the center of this object, so the whole distance there. And the Earth's radius is 6,400 kilometers just to there. Then you got to add 150 more kilometers to get there. And, you know, reminder that you would convert that into meters before you do it. So we can calculate the gravity force acting on this object far away by just using this equation. And of course, G is that constant, is 6.67 times 10 to the minus 11. And that would be Newton meters squared per kilogram squared. Okay, and again, this equation is very useful. It's called the inverse square law. So if we take a look at this, if we increase the mass by a factor of 2 of Earth, then the gravity force will be twice. But if we double the distance between there, it would go down by 4 times, because that's what an inverse square law means. So if radius is doubled, you square that so it goes down by 4 times. Okay, we'll see that again in electricity when we do Coulomb's law. Okay, now what about the orbit of this going around and around and around? We can actually calculate the orbital velocity of that, because we know that the force centripetal must be caused by force gravity. There's not a big long rope making that go around the circle. It's gravity pulling this way. So force gravity going this way. Now remember, force gravity pulling this way is the same that the Earth is feeling back. It's an equal and opposite thing. But of course, we observe the satellite moving, not the Earth, because the satellite doesn't have as much mass. So we're going to use little m for this and big M for the mass of the Earth when we use this equation. So the force centripetal acting on the satellite would be mv squared divided by r. We're going to set that equal to the force of gravity between those two. So it'd be g, big M, little m, divided by r squared. Okay, so there you go. Now we can simplify this by taking the little m's out of the picture. And we can cross off one of the radius values here. And then we see v squared equals gm over r, or the orbital velocity is equal to the square root of g big M divided by r. Now there's all kinds of useful reasons to have such an equation. If I want to put a satellite somewhere above the Earth and we know the radius, I'll know how fast it's got to be going in order to get it there. If I observe satellites going around planets and stars or whatever, I can then use this equation. If I can figure out the velocity of the orbit, I can use this equation to find the unknown mass of the object that's being orbited around. So in other words, I can figure out the mass of Earth if I know the velocity of this going around us. So there you go. One more video to come on some more special cases of rotational dynamics.